So who are we? So we will be co-presenting. Caesar will be the primary presenter. I'm just here to support him. So my name is Michael Simar-Shashua, part of Reliability Solutions. I'm part of the Spartacus division of Reliability Solutions. I'll talk a bit more about Spartacus in a moment. But essentially, I'm a reliability consultant with roughly 5 and a bit years of experience. And I've focused my last five and a bit years in the Spartacus platform, which I'll talk about in a moment, and a lot in the development of maintenance programs. So off of FMEA, failure modes analysis. I'm going to building maintenance programs that will cover lubrication, mechanical inspection, operator asset care, oil analysis, thermography, vibration, ultrasound, and basically it's full tailored programs that essentially I can build. And that's really my expertise and experience. Caesar today is going to be the core presenter. He's got a lot of experience in motors and everything that's instrumentation. So Caesar, who are you?
Yeah, absolutely. Thank you, Mika. Afternoon, everyone. My name is Cesar Fernandez. I am the current live training development manager with Reliability Solutions. A little bit about myself, everyone. I'm a retired U.S. Air Force veteran. You can say that's where I kind of cut my teeth on the precision maintenance side of the world. I started off as a communications navigations technician and got qualified on those aircraft, on everything of all of the above, engines, guidance and controls, electronic warfare. So I had a heavy electrical background. Then I joined up with Reliability Solutions in 2021. I do teach the mechanical domains, electrical reliability, and I also handle a lot of the leadership training also. I do field mentoring with the workforce development across North America, developing a lot of training programs for different companies, which we'll discuss a little bit further here during the webinar. But I am focused on this webinar and kind of what I do, right? Practical troubleshooting, repeat failure reduction, and reliability culture. All right. I'm excited to be with everyone.
Thank you, Caesar. So promise one last slide, and then we're going to focus exactly on the motors that you guys came to see, learn about. But first off, who is Reliability Solutions? So we're a company based in Florida, founded around 2003, so about 23 years. And the company has grown quite a bit from its humble starts. And now our portfolio of offering is basically divided in 4 main categories, which I'll talk about briefly. So the first one, the top left, is the reliability services. It's the development of the maintenance programs, lubrication, operator care, development of your hierarchy, master data. We can follow different kinds of standards and norms depending on what you want and your objectives. ISO 14224, some of the most common ones that we do and develop. Those are the kind of consultation work that we can do for you, with you in collaboration. Then bottom left, we've got the field services. So that's when we send our technicians to your plants and for various kinds of work, all sorts of condition monitoring, vibration, thermography, and so on. We also do more strategic managerial work. So it's going to be focused on the planning, scheduling, project management, shutdown planning. So we offer those services. Top right, skills development. If you guys are here today, it's probably because you're interested in that, as this webinar on motors comes from the Precision Maintenance Guidebook. It's a extract of one of our courses. It's really a summary, but nonetheless, I'm sure we're going to give you a lot of information today that you'll find valuable and you'll be able to take back home. The other thing is, as the labor domain industry evolves, then we're becoming more and more of a skills-based labor market, and developing your skills becomes even more important. So what we offer is skills assessment. What are the gaps at your plant? What do you need? Where's the lacks? And then we can give you those courses. We can give them at our own facilities or at your facilities. Those courses are given. They nearly always have a theory to it, theory portion, of course, but also a very strong hands-on approach where we're going to have the technicians work on machine to perform and execute the work that they've learned through the theory portion of the classes, so that they can go back to their plants, or if it's done at your plant, so that that knowledge can be used and mastered there, and you guys get to use it after. Then bottom right, we have two softwares that we offer. One of them is Lubit, the other one is Spartacus. Lubit is a platform that specializes in lubrication. It is really well tailored to lubrication. It's very precise. You can go quite in detail in it and have the best lubrication program out there. You can build it in Lubit. The Lubit also allows you to execute those PMs, those lubrication routes that you build in there. Spartacus, that's my specialty. It's a web-based platform that has three folds to it. So the first one is development of maintenance program, and that includes vibration, thermal, oil analysis, mechanical route, operator asset care. All of that is covered in Spartacus. Then those can be turned into routes that PMs basically that we're going to execute in the field. Those routes can be executed digitally through Spartacus. And the result of those inspections will create a dashboard, a portrait. Essentially, it allows you to consult those results. And often, most of our customers end up wanting to connect Spartacus to their CMMS so that we can push work orders directly to SAP, Maximo, JDE, you name it. So that's basically what Spartacus, in a nutshell, that's what Spartacus is for. Good. Yeah, can go to the next slide. So I'm going to leave you guys up with Caesar in a moment. I'm just going to answer two questions that will arrive right away. So the first one is, you might notice that that this webinar is being recorded. It is being recorded. You will have access. You will receive basically an email that will give you access to the recording if you so choose to visualize it, especially if you didn't have time to see it all. And if you want to share it with your colleagues, you'll be more than free to share this recording with your colleagues. However, the PowerPoint presentation will not be shared. Also, we are now 74 people in the call. Probably there's going to be a few more later. If you have questions, wonderful. We'll gladly answer them if time allows. You guys know how the Teams raise hand tool works. So if you have a question, raise your hand, and if we can, we will answer those questions. If we can't, once the full hour is through, so once we hit 3 o'clock or 2 o'clock or whatever your time zone is, Caesar and I will stay an extra 30 minutes and answer questions that are more specific, or if we just didn't have time to do it in the whole hour-long webinar presentation. That's it. Caesar, the floor is yours.
All right. Thank you, Mikael. All right, everyone. So in front of you at the moment, you got our agenda for today's webinar. We're going to have 5 main sections here and a final wrap up and QA. But we're going to take a look at why motors matters. Okay. Why good motors still fail. Why reliability is bigger than the motor. Okay. Why finding the root cause is difficult. Troubleshooting best practices. And then we'll end again with that wrap up and QA. Okay. So us here at Reliability Solutions, everyone, we like to begin with our customers. We like to begin to define what is the business problem, okay? Then we challenge those assumptions, and then we show a better way or a better troubleshooting approach, okay? As we go out through today, I'm going to give you a couple of case studies, also some real-world examples that I've personally had throughout the class and some of the experiences I've seen while teaching this motors and motor controls troubleshooting course. So the first section today, let's go ahead and begin with the cost of getting it. Why motor reliability matters. Okay. The point of this section is kind of to shift the attention from motor replacement to total failure cost. All right. So let's start off with these figures that we have up here. 3 numbers every maintenance professional should know. All right. 72%. 72% of our motor systems consume a major share of industrial electricity. Which also means that they represent a major share of our production dependency. Okay. Next one, $10,000 to about $500,000 an hour. This is our typical reported range for many leaders for estimates for downtime. All right. Now, obviously, as you all know, depending on what type of plant you have or what's your industry, et cetera, that number could look a lot smaller. Sometimes it could look bigger. It just depends on what our production's losses are. Okay. Now, That one failure event, saying there they can cost far more than the motor downtime and the lost production included. All right, we're going to look at a couple more figures on this next slide that's going to kind of prove that point. Okay, but we want to talk about, all right, what are all the other hidden costs when that motor goes down? All right, we'll dig a little bit deeper than that in the upcoming slides. Okay, let's start off with a couple of different myths. Okay, and you guys tell if anybody wants to raise your hand here, tell me if you ever heard of them. As I go through them, raise your hand. Okay, but if the motor failed, the motor caused the failure. Okay, we find this not to be true. Okay, most of the time our motors are going to fail because some type of external stressor. Okay, whether this is process controls, environment, or some type of mechanical load. Okay, myth number 2: replacing the motor solves the problem. Here we just want to clarify, a lot of times that replacement, it'll restore operation. Okay, but it doesn't explain why that original failure occurred. All right, we want to get everybody back into that troubleshooting mindset. Okay, identifying root causes and eliminating them. Okay, third myth: the overload trip, so the problem's electrical. Just a quick survey, if you guys could raise your hand, tell me if in your plant, how many times, let's say if you get a work order or work request, is it typical that you all see the E&I technicians are called out first, and the E&I has to prove it's not their problem? Is that typical in your plant? You mind raising your hand? Do you guys, okay, I'm seeing quite a few hands go up. All right, yeah. So what I'm seeing in the chat is typically what I see in the classes. Okay. For us to be able to prove that it's not E&I and actually identify these root causes, we need to get back to world-class troubleshooters. All right. In a nutshell, gentlemen, all right, Reliability Solutions was created in 2003 because of this. Okay. Our co-founders, they found that in industry, all right, in all industries, not just one. Okay. They noticed that we were starting to become parts changers. All right. And we were losing the art of troubleshooting. All right. So a major part of all of our courses is to get back to that troubleshooting, identifying root causes, and eliminating them. All right. So what does one motor failure actually cost? Well, we can start off with the motor replacement. Typically, we see anywhere from about $3,000 to all the way up to $30,000 plus for one motor. All right. But that still may not be the largest cost. We also have to consider labor. All right. Removing, installing, and testing these motors. We typically see about 8 to 24 man hours. Production downtime. This can be hours to days. All right. And of course, emergency freight or expedite sourcing. Okay. Those costs for the emergency freight is typically 25 to 200% cost premium on those delivery services. Okay. Big takeaway from this slide, gentlemen, is a lot of times, okay, the total avoidable cost per event is almost always going to exceed the actual cost of that motor. Okay. The motors are expensive, but I promise you, when we actually look at the cost of what we're losing, it's a lot more than just that motor. So this is going to bring us to our first poll. All right, if you could, you should have a poll popping up in front of you here. What is your biggest motor reliability challenge? Repeat failures, troubleshooting capability, electrical failures, mechanical issues, or control system issues? I'll give everybody a second. Wait for the responses to come in.
I'm sure you guys are all thinking, the question isn't which one, it's which one is the most common, right? You were right, Caesar. That is what you thought. When you said the other day they would pick troubleshooting.
Absolutely. All right. So troubleshooting came out as number 1, correct?
Oh yeah, by a long shot. And I mean, there's also mechanical issues and repeat failures to a lesser extent, but yeah, troubleshooting, mechanical issues. I mean, that's the majority, and it's the same. The troubleshooting is usually the one we see the most all the time.
Absolutely right. So then, if troubleshooting comes out as the main event, and I just kind of want to ask everyone, that kind of ties it directly to either misdiagnosis or inconsistent processes. All right, something to think about as we go down this webinar today. Right now, don't get me wrong, that's not the only reliability challenge, right? The other ones still matter. Normally, our electrical or mechanical control issues. Those we see those in high numbers also. Okay, those are usually going to be connected to. They're usually connected, right? My electrical, mechanical, or control issues, they're usually connected. We shouldn't isolate them too quickly, which we'll dig a little bit deeper here in a second. All right. So let's go on to our section 2, why good motors fail. Motor design has not changed, everyone, for a very long time. The basics of our motor design, it's a pretty solid design, usually very well built, right? However, it's usually, again, usually not the motor, okay? But that motor could be it could be a good motor. It could be properly built, recently installed, and still fail, right? If the system around it creates those damaging conditions. Okay. So I kind of want to start setting a theme here, gentlemen. All right. Often the motor is the victim, right? The motor may be right where the symptom occurs. That doesn't mean that the motor caused failure. We have to look at all these other different factors, fellas, right? Power quality. When we're teaching these classes, fellas, are we generating our own power? Are we getting them from the grid? Do we have capacitor banks? Do we have transformers? Who's maintaining them? Is it us? Is it the techs? Are we hiring outside contractors? All right, but power quality is something that we should be monitoring, all right, and can cause issues with that motor. Voltage imbalance, all right, which could be an issue from our power quality. Single phasing, I know you guys probably deal with that quite often. In this course, we're going to teach you all some things, all right, even after the fact, after a motor fails. What are you doing with your motors, all right? Typically, when I go into a plant, they're usually going to have a standard, for example, hey, every motor 35 horsepower and below goes in the garbage, and everything bigger gets sent out to get rebuilt. All right, what are we doing with our 35 and belows before they go in the trash? Are we opening them up? Are we inspecting them? All right, that's part of that troubleshooting. They might lead us to that root cause. If it died by single phasing, you should be able to ID that on a motor. All right, just by looking at the windings inside. Okay, misalignment, mechanical binding. All right, how we set these motors up. We have long conversations about who's actually putting the motor in. Are we doing precision alignments? Are they trained in precision alignments? Right? If you have mechanics out there who are just throwing motors in with no tools or just kind of eyeballing everything, I promise you our E&I techs are going to get called out for overcurrent situations, or our motors are going to die early. And we think it's a problem with the motor. It could be just misalignment. Okay. Overloading. All right. How do we overload? We're using a motor too small for the design or the process, right? We always want to push more and more product. Okay. Are we overloading? These are all things we need to look at. Process changes, okay, control issues, we'll dig in a little bit more here in a second. Contamination, right? Housekeeping. Can our motors breathe? Are our inlets for the fans blocked? Are the heat sinks covered in whatever it might be, pulp, wood, etc.? Okay, and of course, poor installation. But again, right, the motor may be where the symptom appears, but it doesn't mean that the motor causes a failure a lot of the times. All right. Is it a source or symptom is what we want you to ask, okay? For example, let's just say if we have an overload trip, as you guys see up there, a high motor temperature bearing fault, high current, all right, repeated fuse operation or nuance VFD faults. Again, all of these could be a symptom or a deeper issue, maybe not the actual root cause, okay? Overload tripping. Right. Technically, an overload tripping, it might be that overload is doing its job. All right. It might be an external factor that's causing that high current situation, causing it to blow. Okay. This is why we say troubleshooters think differently than people who simply replace failed parts. Okay. So your average troubleshooter versus your great troubleshooter. All right. Your average troubleshooter may assume, great troubleshooters verify. Okay. Average troubleshooters, they're usually going to focus on getting that machine running, get production going. But your great troubleshooters, they're also going to ask, how do I prevent this from happening again in the future? Okay. Now, a lot of times, and I'm sure you guys can give me a little raise of hands here. How many folks out there feel a lot of pressure or rushed just to get from, could be from production, but we got to get the production going. Do we feel pressured a lot? A lot of times when we're out there on the plant? Okay, yeah, absolutely. Those are typical responses we see in the class. And what we like to say, everyone, sometimes, okay, you have to get the plant running. Sometimes we do have to just, as we like to call them, temporary fix or a Band-Aid. Okay, sometimes it is necessary. The problem is, what are we doing after that temporary fix? Are we ever going back? Let's say, for example, we just had to change a motor to keep production going. What are we doing with that failed motor after we take it out? All right. Are we running any type of motor circuit analysis on it? All right. Do we have any motor circuit analysis equipment for us to do that? That's another big topic that we go through in the class. As you all see here, we're going to talk about data and how modern all of our technology has gotten. What are we using for test equipment? Some plants might not have the budget for some expensive $60,000 PDMA equipment. That's all right. Okay, we'll go over some cheaper equipment that we could use all the way down to LCR meters, right? Looking for impedance between their phases and other things like that. Okay, we'll cover that a little bit later. But all right, evidence drives decisions. Okay, and our assumptions drive repeat failures. Okay, so let's talk about a little real world example I had the other day teaching this class. Okay, we were in Oregon at a food and beverage plant, and we had we started off the course. We started teaching them a lot about this motor circuit analysis and troubleshooting. And one of the students said, "Hey, here's our situation. We had a 200 horsepower compressor motor that started tripping overloads." All right. They went ahead and ordered a new motor. The replacement motor that came in was a 12 lead motor. The old motor was a 9 lead. Okay. The new 12 lead motor went correctly during the installation. So they fired up that motor and it started tripping the overloads again after the restart. After that, the technicians went out, all right, and they ID'd that, hey, it was wired wrong, and they went ahead and corrected the wiring. They fire up the new motor again, and it still was tripping the overloads. By the time we had gotten there and we had started the course, right, they told us the whole story, and they were at a shutdown, so we had the opportunity to go outside to the field. And what we did, I said, hey, everything we just taught you here, we can go down there and troubleshoot that motor. And we did exactly that, right? We took our all test equipment. We were lucky that it was during the shutdown, so they were able to lock it out, make it safe for us. And we went down. We shot that motor at the junction box, and we got bad readings. All right. We had a bad face-to-face resistance, failed our face-to-face resistance checks, and it also failed our current to frequency checks. So after that, we moved from the motor junction box to straight on the motor leads and verified that it was internally in the motor, and that motor had been damaged. Okay. This particular motor was a $12,000 motor. All right. So we were able to prove to them, okay, what we're doing in the class actually works in the real world. Okay. It was very eye-opening for them. It was a very rewarding experience for myself that they get to see, hey, what we're teaching you here actually works. Okay. So they were able to go ahead and order another replacement motor, get it replaced during the shutdown, and they were able to avoid future production losses, right? Okay. So how many failures actually start in the motor? Okay. How many are true internal motor failures? Okay. They're usually probably going to start with some power supply issues, maybe controls, mechanical loading, okay, process changes, installation, or sometimes the environment. All right. You see some images up there, water, moisture, corrosion. All right. They can cause havoc on all of our electrical systems. All right. However, the point is that the answer is often not obvious until we investigate. Okay. So that is why reliability is bigger than the motor. Okay. That brings us to section 3. Which component actually failed? All right. So if we look here, all right, we got utility, distribution, protection, controls, PLC, VFDs. Then we have the motor. Okay. Also the other equipment and the process. All right. which one actually failed first. Okay. When the motor trips, the honest answer is which component failed first. We don't know yet. All right. So sometimes starting at that motor may be necessary, but stopping at that motor in our troubleshooting process is very risky. Okay. So the motor may be where the symptom appears, but the failure may have started somewhere else entirely. Okay. So another thing I do want to mention here is culture. Okay. Culture can affect this also. All right. Let's say, for example, we have a technician who wants to, or they know, hey, we've already changed this motor out 2 or 3 times this year. I believe it's something else causing this motor to fail. And they wanted to go a little bit deeper in the troubleshooting. However, sometimes they may not let them, or everybody's not aligned in that reliability mindset. Okay. That can also drive an issue on finding these root causes for these motor failures. All right. So to troubleshoot effectively, we got to understand how that entire motor system influences reliability. Okay. So power distribution. The healthiest motor in the, yes, sir.
Yeah, just Paul Wiseman's asking regarding your previous slide, or even one before that. So in the end, what was the fundamental cause? Actually, one before that actually why they had to replace the motor, like the in your story, in your example, where you what was the end? What was the end cause of the
Unfortunately, yeah. Okay, so unfortunately, we don't have a reason on why the first motor died because we weren't there. However, that new motor that came in, it was due to a technician incorrectly wiring a 12 lead. So when they first put in the replacement motor, the original motor that was in there was a 9 lead. They got a 12 lead, and that technician made a mistake. All right, and he wired the motor incorrectly. When they fired up, it ran for about another 10 or 15 minutes, tripped an overload, and then by that time, they sent another technicians out and they verified, hey, it's wired wrong, and they rewired it, started it back up. So what damaged it was that first initial incorrect wiring. We were able to spot it afterwards.
If you go one step, it's an accidental mistake or more just a lack of knowledge, lack of experience, training?
Lack of experience.
Yeah. So I mean, just there, that
besides
distant parts, that was $12,000 plus shipping, plus time and labor, plus this and this and this. So just all those costs already, just for that. So the importance of knowing, of knowledge behind it.
Absolutely.
Does that answer, Paul? 100%. Does that answer your question? Well, I guess we'll just we'll continue then. All right.
Yeah. Awesome. Yeah. Great question. So let me get back on. Here we go. All right. I think we left off on power distribution. Right. So one of the things we like to say, everyone, right? The healthiest motor in the plant cannot overcome poor electrical supply. Okay. That voltage imbalance is going to create excessive heat. All right. And efficiency loss. Single phasing, again, remember, is going to be one of the most damaging conditions for our 3-phase motors. Loose connections, they're going to generate heat, voltage drops, intermittent faults. Okay. Then our protection settings matter because the incorrect setting, they're going to create those nuance trips or fail to protect our equipment in the long run. Okay. But power is only one side of the system. Okay. Controls are another major contributor. Okay. So these control systems, they're going to influence reliability, okay, and our troubleshooting decisions. Okay. For example, you got a couple of some examples up here. Contactors, okay, worn contactors, they're going to increase resistance and heat. Okay. Overloads, again, setting correctly, they're going to cause those nuance trips. Control relays and interlocks, they create intermittent or unexpected equipment losses. Okay. But one thing to remember, okay, that motor may be healthy, okay, the controls may not be. All right. And in these modern plants, all right, controls are no longer just a starter or an overload. 30 years ago, typical system, you probably only had a motor, starter, overload, and some type of push button to get everything going. Today, typically what we're seeing, you're going to have PLCs. All right, do we know how to program the logic? all of your VFDs. We're starting to see a lot of DC motors go away and get replaced with VFDs when we have the long conversations on those upgrades, because we are starting to see a lot of electrical fluting from a lot of plants who had DC motors and switched to VFDs just because they did not plan their wiring upgrade in accordance with what these VFDs need. Okay. Networks, remote inputs, outputs, your smart sensors, okay, diagnostics alarms, and your process automation. They make the troubleshooting process a lot more difficult. Okay. Beyond our electrical and control systems, okay, the process itself can create some motor symptoms. Right. A lot of time, these motor failures are frequently driven by the process conditions. Okay. Increased product load. We see this quite often, everyone. Let's say we have a perfectly designed system, right? The correct horsepower motor, the correct gearbox, all right? Everything is good, but we start increasing that product load, all right? There's a chance that we are using our systems out of its original design because of our product load, okay? Mechanical binding, all right? Motor temperature is going to increase on that. Product buildup, we also see a lot of that. And that goes back to that housekeeping I was talking about a little bit earlier. All right, but product buildup on your motor inlets or on the heat sinks on the side of your motors, depending on what type of motor you have, can lead to a lot of issues. Okay. Then, of course, our process changes. Okay. Different consistencies, depending on your industry, can also overload that motor, cause binding, etc. Okay. But with all of these, all right, the next question is, where should the troubleshooting start? All right. Common motor fails, you replace the motor, start the equipment. All right. We want to change that mindset. We want to get you on that reliability approach. All right. Once the motor fails, we want you to start with evidence, collect evidence as much as possible. That means interviewing operators, all right, reviewing CMMSs, getting as much data as possible. Okay, making informed decisions, then investigating the system, identifying the actual root cause, correcting it, and then documenting what was learned. All right, I can't tell everyone in here how much I harp on documentation. Okay, but this approach is going to make sense. All right, because this is going to help us actually identify those root causes and hopefully eliminating them, prevent those reoccurring failures. Okay. All right, that brings us to section 4. All right, why finding the root cause is so hard. All right, so this one we like to call it, a lot of organizations are facing the perfect storm. Okay, what we typically see in today's organizations, you guys are facing 4 main challenges simultaneously. I promise there's a lot more in this, but these are some of the big ones. Right, the workforce challenge. All right, a lot of folks are retiring. We may have high turnover rates, etc. But that experience is leaving faster than it's being replaced. All right. When that happens, we're losing a lot of what we call that tribal knowledge. All right. Reduced mentoring opportunities, smaller maintenance teams also. Or when we get those smaller maintenance teams, you might have those smaller teams with increased responsibility. Okay. Equipment complexity. Here, right, we've always had challenges, but back in the day, the systems were a little bit simpler. All right, there were a lot less variables, technologies, fewer points of failures. With what I mentioned earlier, okay, all of our equipment has gotten very complex, and we got to grow with it. We have to train, all right, to these new systems and new technologies we have. Okay, production pressure. Again, I kind of hit that a little bit earlier. I saw a lot of hands going up, but there's less time to investigate before restoring operations. And we talk about that, right? We have those conversations. Sometimes that is necessary. Sometimes we got to get the process going again, but don't forget to identify that root cause and actually eliminate it. Okay. So has training kept pace with technology? All right. Equipment is constantly getting more complex. The amount of data we are able to collect is getting bigger and bigger every day, which we'll talk a little bit more on the next slide on that one. Production demands or expectations are constantly rising. All right. Are we investing in training? Are we investing in mentoring time, documentation quality? and our standard troubleshooting process. Do we actually have a process in the plant for our standard troubleshooting? Usually the answer I would get on that is no. Okay. Now, we like to say, right, this is a reality check. We're not trying to blame anyone, right? Think about all the data that we collect on a day-to-day, right? Some examples: vibration analysis, infrared thermography, ultrasound, motor circuit analysis, electrical signature analysis, monitoring all of our power quality, PLC diagnostics, VFD diagnostics, and process trends. Okay. All of these are tools that are valuable if used correctly. All right. But the challenge, again, we like to say, is no longer just collecting the data, right? It's knowing what that data means and what decision that data drives. Okay. Without a process, again, all right, more information can just create confusion. Okay. More data, more alarms, more reports, more dashboards, more trends, more opinions. But without a process, what we typically see, all right, evidence usually gets missed, assumptions become facts, symptoms get treated as causes, and we start to see our repeat failures with our motors. All right. So I got another poll for everyone here. All right, let's see how often formal investigation happens in your facility. All right, so the question is, how often do motor failures receive a formal root cause investigation? Always, sometimes, rarely, or never. I'll give everybody a sec.
That's interesting.
Okay.
Never used to be more than 2%, I think. So obviously you can see a sort of like industry trend towards reliability and troubleshooting, even though maybe not as extensive and as thorough as it should be. It is becoming more common. But yeah, the answer, I mean, 51% rarely. That's, the most common case. And that's just earlier, Caesar, you're pointing out, you were showing the chain where you're looking just at the motor. This is really just when you do a root cause on the motor, you're not looking at the peripherals of it that lead to the failure of the motor.
Absolutely. All right. And that's something to think about, right? And there's a little follow-up question for everyone if you guys want to type in the chat. When the same, first off, are you seeing a lot of repeat failures? And if you do, if a failure returns, is it treated as a new event or a repeat? Are we actually classifying repeat or recurring events in your plant?
Maybe they didn't hear you.
Possibly. That's all right. We'll continue.
Failures generally trigger an RCA. No, there wasn't another poll. It was really just a open question for written text. Okay, so you guys repeat. So for you, the trigger to do a motor analysis is whether there is if it's a repeat event. Okay.
Okay, sounds good.
One of the ones we often see is it is based off of the cost. So if it costs production or the company X amount of dollars, that's when we do an RCA, and it is a bit of a it is quite a flawed way of basically deciding when to or not to do a further investigation. I'll let you, Caesar.
Yeah, no, absolutely. I just saw that Wilson put it on there. That's a lot of what I see. RCA is done if downtime is over a certain amount of hours, or like you said, Mikael, a dollar figure is typically what we normally see. However, just kind of keep in the back of your minds, everyone, right? The students that go through this class, we want to change that mindset. Okay. We almost want to get them thinking on root cause failure elimination, almost on everything they touch. All right. So we try to set that mindset. Okay. All right. So that brings us to section 5, everyone. Some best practices. Okay. We have an acronym we use here at Reliability Solutions. It's called, we say we want some nerds. All right. But that's an acronym for notice, investigate, resolve, and document. Okay. But effective troubleshooting, all right, it's going to start with noticing those abnormal conditions. Okay. How do we typically notice in plants? That could be from a work order from an operator during our PM routes. We notice a high temperature, high vibration, et cetera, whatever, high current situation. Those are typically the ways we notice. But when we noticed, right, we want you all to ask a few questions. Take a look at the overall picture, the whole process. What changed? What's different? Is anything abnormal? Who noticed it? Where did it start? What were we doing? Okay, how much output on on our process? All of the above. Okay. Once we notice something abnormal, okay, from here the next step is going to be to investigate. Okay. Here we want you to collect facts before reaching the conclusions. All right. We'll have some conversations in the class on the typical way we think. All right. Whenever, and you guys correct me if I'm wrong, you can raise your hand in the chat if you like. How often is it as soon as anything happens, all right, if we have a write-up or a discrepancy or an unplanned shutdown, one of the first things you're going to see is most folks are going to call out what is wrong. Right? It's got to be this. It's got to be this. It's got to be this. And we will defend that, right, before we collect any data, before we collect any facts, before we look at everything you see on the screen here, operating conditions, failure history, maintenance history. We usually jump to conclusions, and then we tend to defend those conclusions without the facts. So we want to put a pause to that and actually investigate. Okay. Like I said, right, operating conditions, failure history, maintenance history, etc. Collect all before reaching any conclusions. Right. After that, once the evidence points to a cause, next thing we're going to have to do is resolve it. Okay. Correct the problem, not just the symptoms. All right. Some of these resolutions are going to require correcting power issues, adjusting protection settings, repairing mechanical defects, updating control logic, correcting installation practice, or just addressing process conditions. Okay. But do not imply every issue needs a massive RCA. All right. We don't want everybody to run an RCA every day. We do want to get in that root cause elimination mindset. Okay. The depth of an investigation should match the risk and the consequence of the failure. Okay. But the goal is to prevent reoccurring problems. Okay. So after resolve, that's going to take us to our documentation. All right. If we do not document what happened, the organization may have to relearn that same lesson later. I cannot stress everyone here how important the documentation piece is. One thing I like to say when I'm teaching this course is if our documentation is lacking, we are not performing precision maintenance. There's no such thing as precision maintenance without correct documentation. Okay. Again, it's not paperwork, it's proof of learning. Okay. What do we need to capture in our documentation? What happened? Okay. All the evidence and the data we collected, what caused the failure, what corrected it, all right, what prevents the reoccurrence. All right. But I can't stress enough how important that documentation is. During this course specifically, our motors and motor controls troubleshooting course, all right, we talk a lot about the data and what we want to see in that data. If you're using an MCA, right, we give you all your charts. We can provide those to you. If you don't have those in your plant, you don't have those standard operating procedures. Hey, every time we get a brand new motor, even if it comes from the rebuild shop, if it's coming from a rebuild shop, we should expect a few things. That rebuild shop should have a full spec sheet with, all right, a lot of those readings I'm talking about. Then if we have our own, any type of MCA or motor circuit analysis test equipment, we should be checking those motors when as soon as we receive them from the rebuild shop. All right. Then if we have some type of catastrophic failure, we should be checking those too. When we do all these checks, we should be documenting them. All right. When all that documentation, all those numbers should be uploaded to a CMMS. All right. And we should be able to retrieve that data at a later time. Okay. I can talk on documentation for another hour if you want, Mikhail. It's very important in this reliability journey. All right. All right. So why do our repeat failures occur? All right. They're often process failures. Okay. Common reasons: we never identified that root cause, or our lessons learned weren't documented, evidence wasn't collected, knowledge wasn't shared. Okay. Symptoms treated as causes, or corrective actions were never verified. All right. But this is the difference between our parts changers and our troubleshooters. All right. I'm not going to spend too much time on this one. We kind of discovered, we kind of hit this one a little earlier, but I do want to talk a little bit about people and processes and technology. All right. People, they provide the knowledge, experience, right? The judgment, capability, right? Processes, they provide consistency, repeatability, documentation, and standard work. Technology gives us the tools, the data, the diagnostics, and the verification. However, all right, sustainable reliability occurs when all of these work together. All right, this is how these organizations move up. All right, and our reliability maturity, as we like to call it. All right. If we notice here, we have our reactive, preventative, predictive, precision, and reliability. All right. Reactive. And you all, if I had a chance, how many of you all would say your plant is in a reactive state when it comes to maintenance? If you could, just raise hands for me. Okay, quite a few. Yeah, that's what we want to get away from, everyone, right? Our preventative, okay, those are going to be all of our scheduled maintenance, right? Things we're going to do on on a calendar base or an hourly base, usually entail inspections, etc. Our predictive, now we're talking about condition monitoring, right? Condition monitoring, this is where we are going to identify failures, but at very early stages in the life. Okay, we can gain some time here. We're not going to get more downtime to fix the problem. Okay, but we can have more lead time for ordering these hard to get parts. And another one too. Okay, when it comes specifically to these motors and motors troubleshooting, by a show of hands, I'm just curious. How many folks in your plant only have a mega and a multimeter for troubleshooting motors? Just out of curiosity. Okay, now again, can you give me a show of hands on how many folks actually have some type of motor circuit analysis or PDMA equipment for troubleshooting your motors? Quite a bit. Awesome.
But the question is, how many actually use it? Because I've seen
Great.
a lot
Great
where I go
follow-up.
there, they've got one, and they're like, yeah, it's been there, it's been sitting there. We've paid it $20,000, and it's been used once the day we bought it, and since then I've never seen it. I don't even know where it is.
And feel free, everyone, to type in the chat if you wish, if you want to comment on that, because you're absolutely right, Mikhail. Absolutely. Or what I've also seen is there's only one guy who knows how to use it, and he's only there. Would prefer not to recommend as often to do MCA. Gotcha, Jeff.
I think it's important to look at all this motor analysis that you do when you collect information. We're going to tackle not necessarily reactive, preventive, or predictive. It's really tackling precision. The goal is to be able to eliminate the potential defects at the start. So not necessarily giving you more time when you find a problem, but just reducing the number of problems in the first place. Right. And that's really the core reason you're actually doing a full analysis in the first place. If you have the skill set and if the leadership at the plant actually pushes forward this mentality of taking the time, resource to actually do those proper full investigations.
Absolutely. what we like to say too, Mikael, right? Let's take your Megger, for example, that I was asking about. If you fail a Megger test, we consider a Megger as a go, no-go test. All right. If my motor fails a Megger test, I have reached the end of the line, right? I am short route. Usually, all right, not always, but most of the time, that failure or that short to ground began as a turn to turn or face to face or coil to coil, etc. Meaning, hey, instead of that motor completely stopping production, maybe I could have spotted this failure at the beginning stages 4 months ago when it was a turn to turn failure, right? So now what does that get me? That again, that's that lead time. Hey, we got to get a new motor on hand. All right. We get that ball rolling. We already know it has an issue internally in the motor. We're starting to see that impedance imbalance, or we're starting to see that current frequency failure on it, pointing to something is wrong internally in that motor. All right. Now we can plan though. Avoid that unscheduled downtime. What are we going to plan? Manning, downtime, all right, parts, etc. Okay, so they can help you quite a bit, everyone. All right, Mikael, I think we're getting a little close to the time. That takes us to our wrap up, everyone. Okay. The goal, again, everyone here, okay, it's not to simply have more training. Okay. The major goal here is to develop world-class troubleshooters. Okay. How do we do that? Structured training, hands-on practice, field mentoring, coaching, knowledge transfer, repetition, and documentation. Now, all right, that's the purpose behind that motor and motor control troubleshooting. All right, but I do want to kind of let everybody know here. All right, Reliability Solutions is we're taking a different approach more and more these days, where we're not just giving you a training class. Don't get me wrong. If we need the training, we'll be there. We'll absolutely execute all the training you want. But it seems we are taking more approach to where we are more of a partnership, where a lot of times when we teach a class, the following week or the next day, we're going into the field with you and we're mentoring you, helping you apply everything you learned in the class to your plant specifically. Okay. Also training programs, OJT programs, determining, what a level 1, a level 2, level 3, if that's what you have in your plant, should know any gaps between any training programs. That's what we're here to do, everyone. Okay. So typical challenge we address, again, repeat motor failures. All right. Long troubleshooting time, limited documentation. But this motors and motors control courses, all right, focuses on our motor systems, motor controls, our testing technologies, failure simulations. We do have, remember everyone, we are about 50% of lecture and 50% hands-on. So we bring 6 motors out there with faults on it that you will troubleshoot. We also have a controls demo unit that you guys will troubleshoot, and you will do some PLC logic training in that class also. Okay. So to end it up, gentlemen, our key takeaways. All right. Number 1, the motor is often the victim, not the cause. Reliability is bigger than the motor. Troubleshooting requires evidence, not assumptions. Data improves decisions when it's used through a process. Right? Documentation prevents every failure from becoming new again. And people, process, technology drive sustainable reliability. All right. So again, next steps, go deeper with our hands-on training. Okay. Remember, we support you with our motors and motors control troubleshooting training, our skills assessment. I believe Mikael mentioned that in the beginning. All right. Field mentoring, reliability consulting, and of course, our workforce development programs. All right, everyone. That's going to be the end of my soapbox unless you guys have any questions. But I do want to say thank you, everyone, for attending and appreciate having everyone here today. Mikael, I'll hand it over to you.
Perfect. Thank you, everyone. I hope you enjoyed it. I hope it answered some of your questions and then maybe shed some light on maybe where you are today and where you need, what are the next needs or objectives you may want to focus on. For those of you that have questions, we'll stay on the call for 30 minutes. And as a reminder, if you guys want to share this webinar with some of your colleagues and so on, you're going to receive in a few days you're going to receive an email with a link to the recording so you can share it with your colleagues. And yeah, so thank you for your time.